Hello class, today we're going to discuss spherical mirrors. Spherical mirrors are shaped like sections of a sphere and may be reflective on either the inside, which is called a concave, or the outside, which is called convex. Concave mirrors are used for shaving or cosmetic mirrors, and then convex mirrors are sometimes used on cars or trucks as a rear view mirror and in shops for like thefts. Because they take in a wide field of view. Now let's consider an object that is very far from a concave mirror. The rays coming from a faraway object that strike the mirror are nearly parallel. For an object infinity far away, kind of like the sun or stars, the rays would be precisely parallel. Parallel rays striking a spherical mirror do not all converge at the exactly same place if the curvature of the mirror is large. This is called a spherical aberration, and the image is blurred or not sharp. Now, if the curvature is small, the focus is much more precise, and the focal point is where the rays converge, and the image is sharp. In the case shown, the incoming rays are parallel to the principal axis, which is defined as a straight line perpendicular to the curved surface at its center. Now point F, where the incident parallel rays come to a focus after reflection, is called the focal point of the mirror. And the distance between F and the center of the mirror is called the focal length, little f, of the mirror. And then point C is the center of the curvature of the mirror, and so the dashed line equals the radius of the curvature. Now notice that the incoming ray at point B follows the law of reflection, with the radius acting as the normal at that particular point. Also notice that the angle BCF equals CBF, and thus the length CF equals FB. And since we assume small angles, the length FB is nearly equal to the length FA, which is the focal length. So thus, the focal length is half the radius of the curvature. This is only with the assumption that we're using small angles. Now we saw for an object at infinity, the image is located at a focal point of the concave spherical mirror, where f equals r over 2. But where does the image lie for an object that's not at infinity? Well, first consider an object as shown as an arrow and is placed between f and c at point O. Let us determine where the image will be for a given point, say O prime, at the top of an object, by finding the point where rays are drawn from the tip of the arrow converging after reflecting from the mirror. To do this, we can draw several rays and make sure that these reflect from the mirror in such that the angle of reflection equals the angle of incident. Now in figure A, ray 1 goes out parallel to the axis and reflects through point F. In figure B, ray 2 goes through point F and then reflects back parallel to the axis. Now we could stop here, but we'll do one more ray. In figure C, ray 3 is perpendicular to the mirror, and so it must reflect back on itself and go through point C. Note that all three of these rays leave from point O prime, the top of the object. After reflection from the mirror, the point at which these rays cross is the image point, which I prime. All of the rays from the same object will also pass through the image point. Note that the bottom of the arrow on the principal axis is point O, and the image on the axis is at point I. Now, with these 2 points, I and I prime, a complete image of the object is formed. Now, because light actually passes through the image, this is a real image, and that will appear on a white surface or film if it's placed there. This can be compared to a virtual image, which is formed by a plane mirror where the light does not pass through that image. Also note that the image in figure C can be seen by the eye only when the eye is placed to the left of the image, so that some of the rays diverging from each point on the image can enter the eye. Now geometrically, we can derive an equation that relates the object's distance, image distance, and focal length of the mirror. D naught is the object's distance, d sub I is the image distance, f is the focal length, and this equation is called the mirror equation, and this is where we assume f is half the radius. The magnification m of the mirror is defined as the height of the image, h sub I, divided by the height of the object, h sub naught. If m is negative, then the image is inverted. If positive, then upright. Similarly, if the image h sub I is positive, then the image is upright, and vice versa. And lastly, if d sub I or d naught is positive, if the image is in front of the mirror, and if di is negative, then the image is behind the mirror. Okay, so for our first example, we have a 1.5 centimeter high object that is placed 20 centimeters from a concave mirror with a radius of curvature of 30 centimeters. We want to determine the position of the image and its size. We'll use this figure as a reference. The first step is to find the focal length by dividing the radius by 2. With the radius curvature of 30 centimeters, the focal length is 15 centimeters. Next, we'll use the mirror equation to find the image distance. Rearrange this equation to solve for the image distance. We know the focal length is, we know the focal length is 15 centimeters and the object's distance is 20 centimeters. Plug and chug to get 0.0167. But this is not the final answer yet. We need to take the reciprocal to get an answer of 60 centimeters as the image distance. Now to find the image height, we'll use this equation. Rearrange the equation to solve for the image height. We know the image distance from part A. The object distance is given as well as the object's height. And we just plug and chug, and we get an image height of negative 4.5 centimeters. The negative sign means that the image is inverted. Now, if the object is below is placed instead where the image is, where will the new image be? Well, the mirror equation is symmetric in that d naught and di. Thus, the new image will be where the old object was, and the direction of the rays are reversed. Now, if an object is inside the focal point, its image will be upright, larger, and virtual. Whereas before, when the object was in between the center and focal point, the image was inverted, still larger, but also real. So here we have a 1 centimeter high object. It's placed 10 centimeters from the concave mirror, whose radius is 30 centimeters. And for part A, we want to draw a diagram to locate approximately where the position of the image is. And then part B will determine the position of the image and the magnification analytically. Now for the ray diagram, all 3 rays will start from the top of the object. Ray 1 is parallel to the axis, then reflects through the focal point. Notice that the dashed line is extended behind the mirror from the reflected ray 1. The incident of ray 2 needs to line up with the focal point and the top of the object, which extends to the mirror. From there, the reflected ray is parallel to the axis, and the dashed line is extended behind the mirror from the reflected ray 2. And then lastly, ray 3 incident needs to line up with the center point and the top of the object, which extends to the mirror. Then the reflected ray 3 will reflect along the same line, and again the dashed line is drawn behind the mirror, extended from the reflection of ray 3. Where the dashed lines intersect is our virtual image. For part B, again, the first step is to solve for the focal length. With a radius curvature of 30 centimeters, the focal length is 15 centimeters. Then we'll apply the mirror equation, rearrange it to solve for the image distance. We know the focal length is 15 centimeters, the object's distance is now 10 centimeters. Plug and chug to get 0.0333. Then we'll take the reciprocal to get the image distance to be negative 30 centimeters. The negative sign refers to behind the mirror. Since the image is behind the mirror, the image is virtual. Now we'll use this equation for magnification. We know the image distance is -30 centimeters, and the object distance is +10 centimeters. Plug and chug to get a magnification of the image to be 3 times larger than the object. And since it's positive, it means it is upright. Now, if the object is outside the center of the curvature of a concave mirror, its image will be inverted, smaller, and real. If we have a convex mirror, the image is always virtual, upright, and smaller. In this example, we have an external rearview car mirror, which is convex with the radius curvature of 16 centimeters. We want to determine the location of the image and its magnification of an object 10 meters from the mirror. Again, the first step is to solve for the focal length, but notice that the radius is negative because it's behind the mirror, and therefore the focal length is also negative and located behind the mirror. We'll use the mirror equation, rearrange it to solve for the image distance. The focal length is -8 meters, and the object is +10 meters because it is in front of the mirror. Plug and chug to get -0.225. Now take the reciprocal to get -4.4 meters as the image distance. The negative refers to the image locating behind the mirror, and therefore it is virtual. For magnification, we'll use this equation. The image distance is -4.4 meters, the object distance is +10 meters, and the magnification image is 0.44 of the object. So it's smaller than the object's height and upright since the magnification is positive.